Hello, everyone, and welcome to today's live broadcast, AnIML and SiLA, Enabling Integration in the Lab of the Future, presented by Burkhard Schaefer, President at BSSN Software. I'm Alexis Carlos of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. We'll answer as many of your questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, please click on the Help Desk button located in the promotional board at the bottom center of your screen, or use the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Burkhard Schaefer. I will now turn the presentation over to him.
Thanks, Alexis, and thanks for the invitation to be with you here today. AnIML and SiLA, Enabling Integration in the Lab of the Future. So what are we going to talk about? We see all of those efforts for digitization and Lab 4.0 and all of those bits and pieces where we are trying to modernize and digitize the way we are doing things in the lab. But there are a lot of challenges. The first one being, well, we keep speaking about this lab of the future thing, but what is it actually? And what could it deliver for us? And that's actually what I want to start with in the presentation today. And then look at how can we get there? And part of that is connectivity and interoperability. So how do I get all of the different pieces in my lab connected and talking to each other? And we'll be exploring two interesting efforts, the AnIML project and the SiLA consortium, that enable that type of interoperability. AnIML from the data side, being a data standard that's driven by ASTM, and SiLA, a set of communication protocols that comes from the SiLA consortium. Both are fully open and royalty-free, and they've been gaining quite a bit of traction recently. So I want to help you put the different puzzle pieces together and help you at least get a bit closer to this vision of Lab of the Future. So having said that, let's dive right in. And first thing, what is the Lab of the Future and why would I want one? So what do I expect? And obviously there are different definitions, and I'll share my personal one with you. And yours may be different, and please feel free to comment in the Q&A panel if you want to join on the discussion. So what can the Lab of the Future deliver? And I've grouped these ideas around four core points here. The first one is easy provisioning, so that I can set things up and move things around and get going. So the time before I can do my first experiment is as small as possible. The second one is scientific focus. It means people should be focusing on getting their science done rather than moving data around and all of it. And the lab should help me do my things, so I need to worry less around those routine tasks. The third one being connectivity. So I have the different bits and pieces in my lab, the different instruments, my different data systems, maybe a LIMS and an ELN. They need to talk. How do I do that? And the fourth, sustainability, so that my investment that I make into those components today is protected and I have a way for growing. So let's explore each of those four in more detail and see what's behind it. And again, it's my personal definition. Feel free to jump in and discuss. So the first point here is provisioning. How do I actually set up my lab? And with Lab of the Future, people often associate this thought of an agile and flexible deployment approach. So I can go and mix and match equipment from different vendors with different measurement techniques and bring together them in a best of breed approach. So I can get my science done and not have to worry too much about getting everything set up and provisioned and connected to each other. And we hope the lab of the future is going to make that job of getting set up and integrated easier. Second one is scientific focus. So we want to make sure that we let the user in the lab focus on getting the science done, because that's really why we have the lab in the first place, right? We want to take everything else out of the way, and we don't want any more clumsy tools. Now, we all love Excel and cutting and pasting, but please not too much of that. So we can do much better. We can do things like automatically capturing the data, be it from the instrument or be it from devices that are around me. I want still, despite that support that I get from my digital environment, I still want freedom to innovate on the R&D side. But if I'm on the QC side, I'm more into guidance. So I want that guidance to be there and present, but unobtrusive. So that, again, it doesn't get in the way, but it helps me get stuff done. So I can focus. And part of that focus is also making sure that I have everything that I need, so that replenishment of any supplies or consumables that I have happens automatically, or I get reminded when I run low on something that I need. So that's scientific focus for me. Next one is connectivity. And connectivity is about sharing all the data with all the stakeholders. And those stakeholders would be end users. Yeah? They want the result. Yeah? And then data systems like my LIMS, my ELN, or my data analytics and visualization suites, which I use to analyze the work that I've done and share it with other people. And one thing to remember is the data that we are generating out of a lab experiment typically is the most important asset that we generate from that investment, in time and money and all of it. So that's the reason why that experiment is being done, because I want the results. So we need to make that data accessible. And we need to share that data with everyone who needs it. And that means we need to connect with people who want that data. We need to connect with organizations, because that data might actually be of interest to a customer of mine or to a collaborator, either in my organization or elsewhere. Or I may be living in a contract lab and providing service to others. And then also connecting systems so that the data can flow between those systems without too much manual intervention, because that means a waste of time. But also, I want to make sure if I have that system-to-system connectivity, it's easier to get a higher level of data integrity. And connectivity is a nice buzzword, but how do I get that? And we want to talk about that in particular today. And there, to make the interfacing and connectivity easier, standards can be a great tool. So we're thinking about using instrument control standards such as SiLA, or data standards such as AnIML, and we'll be talking about these a bit more. So that's the third one on the lab of the future benefits, right? This connectivity side of things. Number 4, sustainability. And sustainability means, well, on the one hand, when I do my experiment, I'm doing it to generate that immediate result that I wanted. So this was the reason why I went into the lab in the first place. But there may be other ways of using that data, and I want to be ready for that as well. I might want to analyze that data later. And being sustainable means I get not only to reuse my data, but also to reuse my tools. And ideally, I can do that across vendors and measurement techniques. And that would then allow me to reuse and repurpose my data more easily. And if I add context to my data and annotating it, I can enable smart queries, so I can find that information again and draw new conclusions out of it or see trends. And sometimes the regulators ask me to keep my data around for the long term. And our friends in the pharmaceutical industry know what that's like, that others are also regulated in some way, shape or form. And long-term retention of that data is also a very important aspect. And if we set up our lab of the future properly, we can kill quite a few birds with one stone. And we've talked about the connectivity, we've talked about the sustainability, we've talked about the scientific focus. And if we use standards to connect the things, then those things become easier to achieve. So far about this lab of the future ideas and the goals behind this. So how do we actually get there? How can we achieve this? And in order to understand that a bit more, I will tell you first how it's being done today. And you may recognize some of those phenomena here. So the traditional integration between, let's say, a LIMS system, a lab information management system, and an instrument. So in the LIMS, I have an order, and that order should be executed. So I want this sample analyzed, and then I have the instrument that has the capability to do it. So what typically happens is I create my sample in the LIMS and so on, and then the LIMS creates a work list file. That work list file is specific to the instrument that I want to talk to, and it drops that work list file into a folder. Now the instrument software keeps watching that folder, and it keeps watching and watching, hoping for a file to come, then hoping that in the moment I read it, it's actually already written and not still in progress. And then at some point, there's a file here. I'm going to go and grab it, and I perform the run. So the instrument software performs the run now, and once it's done, well, hopefully it gets done, because if there are any errors, I have no way of knowing. Once it's done, it's going to drop a proprietary result data file in some other directory. So just by watching that directory, I get a clue, okay, the sample is probably done. And then I go and poll that folder from the LIMS side. So the LIMS polls the folder, and then hopefully once that file is completed, it picks up the result file. And it doesn't pick it up just before it finished writing the last few kilobytes. And then I have a broken file. Okay, so so this will work, and then the LIMS goes, picks up the result files. This is going to be a different result file for every instrument, so I will have to configure my LIMS specifically to understand that file type and all of that. So so that's one way of doing it. Another alternative approach here is the instrument software generates a PDF report. This PDF report is stored in some repository, such as the Scientific Data Management System, or SDMS. And then we have a tool that parses that PDF. Yes, they do optical character recognition on the PDF to pull out values and then populate the LIMS with that. So not ideal, but this is pretty much how it's being done today to a fairly large degree. And we can do better. So the first thing is, why these files? We need to get rid of these files. We need to make sure that we get a proper control flow and a proper data flow going, so that it's not a fragile construct where I drop a file, I hope something will happen. I have no idea whether the other system is actually running. I just hope it's running and picks up the file, does the work, and eventually comes back to me. There is no status information. There are no events. I can't send a command to that instrument. And when I get the data back, that data is in all kinds of formats. So it's really hard to use that data down the stream. So what's our learning from this? Well, if I want to do true integration, I need two things. On the one hand, I need communication, and dropping files somewhere is not communication. So we need a proper communication protocol in place there. We'll talk about how we do that. And the second one is data representation. So I need one common way, ideally, for representing that data, so that I have an easier way of consuming that data downstream. And I think standards can help a lot with that, and we'll see how. So here is an example of another type of integration. So in this case, we have a balance that we are connecting to a LIMS. It could be an ELN, could be other systems. I'm using the LIMS as an example here. So in a proprietary world, which is the world of today, the balance vendor will publish, hopefully, a proprietary protocol that then the LIMS vendor can pick up and implement and write a driver for it. And then the driver will speak that proprietary protocol that the balance understands, and they can go back and forth, and then that works. Then the LIMS is connected to the balance. But for the next device, the LIMS company will have to write yet another driver. Now, if I want to reuse that same device that I already have connected to my LIMS, but use it from my ELN. Well, the ELN has a completely different driver architecture, so I can't reuse the driver. So it's really a one-to-one connection that I build all the time. And from a total cost of ownership perspective, that's a nightmare, right? But still, we do it. We do it because that is the status quo. And that's what we are working on changing with SiLA and AnIML. So if we go along with this true integration idea, we realize very quickly that communication and data really need each other. Why is that? Well, let's say I had an open communication protocol that I could use to speak to any instrument out there. And I could connect to it, let's say over the network. I can ask it, what kind of commands do you have? Yeah, and then I send the commands. This is all nice and good. But once I get my results back, the data is going to end up in a silo because I don't have a common file format. If I only use a communication protocol, my data ends up in silos again, which I don't want. So if I in turn look at a file format, so let's say I had a data standard that describes a file format. Well, a file format alone is not suitable for components that need to communicate. Yeah? And we've just seen that. You drop a file, you wait for it to get picked up eventually and worked on. Yeah, that's not enough. And copying files around is not communication. So we really need both for proper end-to-end integration. So if I want true integration, I need two things. We've established that. I need communication. And for communication, I use communication standards so that I don't have to write a separate driver for each instrument. And for data exchange, I use data standards so that I don't have to pass a different data format for every instrument that I want to receive data from or send data to. So a good example of two standardization efforts that work together very closely, by the way, is the SiLA consortium, which is creating communication standards, and the AnIML effort at ASTM, which is standardizing data formats for scientific instruments. And I'll be talking about both of these, and then we'll look a bit at how these can get used in order to build a system that actually communicates. So SiLA, many of you will have heard about it. SiLA is an organization that creates standards in laboratory automation, as the acronym SiLA suggests. And what SiLA does primarily is it standardizes a communication protocol. And that communication protocol is network-based. It uses modern web technologies such as HTTP2 and a number of other cutting-edge technologies. And what that allows me to do is to have services in the lab. And those services are provided by, let's say, an instrument or by a LIMS system or by something else that can do something for me. And then I have a way of talking to those services over the network, and I can ask them, well, what type of service do you offer? What are you? And then there are some common functionalities that a typical instrument would have. So if we stick to the balance example, well, a balance would probably be able to tell me the weight, or it would expose a tare function, or it would allow me to calibrate. And depending on the instrument type, those commands would be different. Yeah? And SiLA calls this a feature. Yeah? And a feature is a set of standard commands that a certain type of instrument offers. So a balance would have a particular set of commands. An HPLC would have a different one. An NMR would have a different one. And the Microplate reader would have a different one. And so what SiLA does is two things. On the one hand, the communication protocol, but also those standardized commands for some common capabilities. But on top of that, vendors and users are able to also use additional commands that are not part of the standard and still use as a communication infrastructure for that. So if a vendor has additional capabilities in an instrument and wants to expose those capabilities using custom SiLA commands, they can do that. And this will not break compatibility with other applications, which is quite interesting. And so these features, they grow over time, and it's an open process. Anyone can contribute to features like that. If you think there should be a communication protocol for talking to instrument X, you can join the effort and actually help build it. And you see, SiLA is really about communication, but you need to remember that this is also about data. The lab is also about producing data, and SiLA doesn't address that, which is why there is a partnership between SiLA and the AnIML effort at ASTM, where AnIML is looking after the data format, and SiLA can then be used as an envelope to communicate that data between an instrument and a system. So you use SiLA to talk to the instrument to get it to do the things you want it to do, and then you get a data package back in AnIML format, which is XML-based, and then you can use that data. And SiLA has about 1,700 individuals as members and a number of corporate members, a couple of dozen. And it's primarily active in Europe and North America. And there's a website if you want to learn more. It's a very active community. And that's about SiLA. So next up, we'll talk about AnIML. Now, just like SiLA, AnIML is an acronym. Anything decent is an acronym these days. So AnIML stands for Analytical Information Markup Language. And it comes from ASTM. It's an XML format for analytical data. It's also being used in the biologics space, and was built by a consortium of industry, academia, vendors, and government bodies. And this means a very broad set of stakeholders. And it can be hard to reach consensus, and so that took quite a while to build. In fact, it took them over 10 years to do so. But now you have agreement on what such a data structure needs to be to support all of those different use cases that these different stakeholder groups have. And each member has the same rights. So this effort is not dominated by a particular industry or by vendors or by certain particular groups of interest, but there's an equal and level playing field. And ASTM is good at managing that. And what AnIML allows us is to capture data from a number of different analytical techniques. So it's not a format that can just deal with one type of instrument. It allows me to put the data of any type of instrument in there. And I can combine these different analytical techniques in the same file even. So if I have a sample and I run, let's say, mass spec on it and NMR, and I also take a picture with a microscope, all those three items can go into the same AnIML document and can all be viewed using the same piece of software, which is very powerful. It means that I get to reuse the tools that I have for many more instruments than today. And today, classically, my instrument software only works with that instrument that it came with, right? And having vendor-neutral software packages is quite a challenge. But with a standard like this, it suddenly becomes a reality. And we are seeing that being picked up. So AnIML not only supports capturing results, but also capturing of sample and process data. That's important, so you get reproducibility. So not only does it store your chromatograms and your peak tables and your calibration curves and all that, but it also captures information about the sample, about how you set up the process, the method, the instrument configuration, the instrument serial number, the operator, the software you used, and many things like that. So you have reproducibility and also traceability. And for the regulated communities, there are audit trails and digital signatures, and also validation capabilities built in, so that these types of data sets can then also be used in a regulated environment. And what AnIML is focusing on is accessibility and easy adoption. So we have stories where companies have been able to implement AnIML within a day. And in particular, LIMS vendors or instrument vendors, they just looked at it. They looked at a couple of examples, and then it was really easy to pick up and to get going. And if a standard does that, and if it has a really low barrier of entry, then it can be successful. And especially for data formats, the accessibility is very important because, if we remember, data is the most important asset that we generate out of lab experimentation, right? It's the results that we care about. So making them accessible, that's also part of the mission here. All right. So if there are any questions, feel free to jump in on the conversation and put those into the Q&A panel, and we'll take a subset of these and then answer them at the end of the session. All right, we've heard about these two families of standards that complement each other very well. Let's move on to using them to actually solve the integration challenge in the lab of the future. And this brings all of those things together so that I can focus on getting stuff done. So it's about the connectivity, it's about the sustainability of my infrastructure and my data. So let's take a look. We've talked earlier about how we would use a proprietary approach to connect a LIMS to a balance and so on. Let's try to do the same again, but let's make it a bit more complicated, but this time use standards to solve the problem much more elegantly. And in this case, we'll be using SiLA and AnIML. So at the top here, I've got my LIMS system, and the LIMS system is supposed to interact with the instruments in the lab because I've got some samples set up. So when I configure my LIMS, what I will do is I will ask the LIMS to perform SiLA discovery. So discovery is a feature that's built into SiLA, and that means it can go around the network and see what instruments are there. I don't have to use discovery. I can also simply configure the instruments manually, but it's a bit like a printer driver where you plug in the USB cable of your printer, and then it sees, aha, this is the device, and it downloads the driver automatically, and you don't have to do anything to get it running. So it's this type of discovery where the LIMS scans for instruments or for SiLA services that can do things. And then those different services will respond. So these respond and they say, yes, I'm here. And so we hear about a balance and we hear about a chromatography data system. They pop up. And so the LIMS it becomes aware that they exist. So the LIMS has done the discovery, and the instruments and services have responded. Now the LIMS can go and inquire about the capabilities. And those capabilities are described in features on the SiLA side. And each feature basically defines a set of commands for getting something done. And a balance, we see that on the lower left-hand side, might offer a number of SiLA features such as device information. I can get the serial number, the vendor, the model, and so on. But it might also offer a weighing feature, so I can get the current weight, or I might have a way to target feature where I say, help the user weigh in 1 milligram of a substance plus minus n%. Or there may be a feature to control the door, opening and closing it. And for the chromatography data system, there may be different aspects, different features that I would want. So there could be, again, the device information. So I can see, aha, I'm talking to this and this chromatography data system in this version. I may have a sample submission feature so that I can send samples and create a batch or a run list in that CDS. It's actually very interesting to connect the CDS to a LIMS that way. And then there is a batch status feature that would allow me to control the status of the batch to see, aha, which sample is already done, which one isn't. So I don't have to sit around waiting for files to appear, but I can actually get events and see in real time, aha, these are the things that are going on. So the LIMS is always in the picture. And it's much, much more robust than the traditional types of integration that we used to do in the past. And then there may be access to an audit trail and so on. Now, the SiLA features describe the commands. Now, we also need to describe the data that comes and documents the execution of that experiment. So that's where the AnIML standard brings a concept called technique definitions. And the technique definition describes how to organize an AnIML data set for a particular measurement technique. So a balance would use the weighing technique. So you would know when was it last calibrated, what was the weight that was measured, what was the tare value, was it stable, and a number of other things, and also the settings that were active on the balance, why that was the case. And in the chromatography data system, there would be different techniques that make sense here. So AnIML provides ways of describing chromatograms and spectra. So there could be the chromatography technique, a UV-Vis technique, mass spec, FID, a lot of detector techniques. There's like a dozen of them that would then describe the data, but not just the results, but potentially also the method and the settings and so on, so that, again, I have reproducibility. So the LIMS looks at this, right? Because we're still wearing the LIMS hat. So we're talking to the balance, and we're hearing, this is what I can do. And that way, the LIMS learns how to communicate with it. It can look at the SiLA features, and that allows the LIMS to create those commands and send them, and to discover those commands on the fly. And we also learn about the data structures, which the instrument can support, and the structures of the results. So that's a way of setting up these interfaces without a lot of custom code and huge projects to do the integration. Here you can really discover the capability of an instrument, see what its data look like, and directly map that into your workflow. And that's a big benefit, obviously. And from an integration perspective, that's really, to me, is lab of the future. So what I can do now that I have learned from my instruments what they can do and how to talk to them, I go to stage 5, where the LIMS actually performs the instrument control or submits samples, gets the results, and so on. And we use the SiLA protocol for the communication, and we use AnIML as the data transfer vehicle. And what's nice that once I'm done with an experiment, the service can return a complete and traceable AnIML data package describing what that service did when it was executing that command. And that gives me a complete picture and visibility into what actually happened. So this is a way of executing these types of interactions very, very efficiently. And since nowhere in this concept a file ever hits the disk where it could get lost and where a folder has to be monitored, I have a very high degree of data integrity. And from a compliance perspective, this is also much preferable. All right, so, but now we've focused on this communication between the LIMS and the instrument. Obviously, there's much more, because once I've done my experiments, well, I now have these data packages that describe what I did. So I could do interesting additional things on top of that. So let's look at what that could be. And here we see that the LIMS or other tools could then publish a holistic picture of the outcome of experiments to a global data lake, where I can then go and navigate that data, mine that data, recognize trends, but also archive it for the long term. And this is a very cheap side effect that I get from setting up my system integration that way. I get full traceability, and I can repurpose the data packages that I generate here for many different other purposes. And this is already being done today. So we're not just talking about some future vision or so, but everything here is actually working. And I want to show you what that looks like in practice. So I looked around a little and looked at, well, what kind of measurement techniques could we use as an example? And I found these AnIML measurement techniques. So these are the techniques that I personally know are getting used already with AnIML in production today. This is beyond proof of concept. This is in use. And I've divided them into 3 categories. The first one on the left, the analytical chemistry side. Then in the middle, more of the biologics domain. And then on the right hand, the more orthogonal techniques that are universally applicable. And we can see that in analytical chemistry, we have things like HPLC, GC, UV-Vis, infrared, Raman, mass spec, NMR, and so on. So the big analytical techniques, we've seen all these. In the biologic space, this concept has been applied to bioreactors, microbioreactors, plate-based assays or cell counters, bioanalyzers, and purification. So you actually have people that are using this to model out an entire bioprocess development pipeline and creating digital batch records out of this. And then on the right-hand side, we have things like balances, pH meters, imaging devices such as microscopes or cameras, pipetting, liquid handling, densities, the density measurements, viscosity, and so on. So those obviously fit into many different application domains. And so what I've done is I've looked around and collected a couple of data sets, converted those to AnIML using tools that were available off the shelf, and then and now we can actually look at these. So I'm using some of the tools that we make in my day job in order to render that content on the screen, so we can actually look at that XML content more conveniently. And so now let's look at what some of that data looks like. So here we've got an HPLC chromatogram with a UV detector. In this case, the data came from Chromeleon. And you can see that there's the chromatogram. You can see the peaks are highlighted, they are annotated. All of that comes across. I can switch to the method, I can switch to the sample view. I've got a bit more on what that additional contextual metadata looks like in some later slides. And now I can look at my chromatograms, no matter which software they came from or which instrument they came from, use the same tool to view them, to report them. And this is web-based. There are also desktop viewers available. There are mobile apps available that can be used. So this is just one example. And there are other people who make them too. So this is what UV-Vis looks like. So this is a file that originally comes from a Perkin-Elmer UV spectrometer. And you can see the spectrum at the top. And below, I'm not sure how big your screen is and how well this gets across. You see the metadata. In this case, those were the instrument settings broken down into categories. And that way you knew how the spectrum was shot. And then on the right-hand side, you can see some additional attributes on the sample. Those were taken from the limbs and merged into that AnIML data set so that I get a more complete data package. And this can then be stored and published and, again, used outside of the instrument software. And if I have a LIMS that understands AnIML, and there are quite a few by now that do, then I can do quite interesting things. So that's UV-Vis. This is a Microplate assay. And this is a data set that comes from a Perkin-Elmer Envision reader. And you can see I'm looking at that in my web browser. I have the color coding of my plates, so I can configure how I want that displayed. I have metadata behind each well, and I have the full method of how the plate reader was configured. And you can even buy plate reader software today that already makes these AnIML files. I think Thermo has that in their ScanIt software. Raman, another example, Raman spectrometry. This data comes from Analyze IQ Lab. And in this case, I have an AnIML document which contains 5 different Raman spectra for a calibration scheme to train a chemometric model. So Analyze IQ makes chemometrics tools. And here I've got all of those spectra in a single AnIML file. And I have trained my model with it. And I can now have that model executed. And the result could also go into an AnIML document. So this is also a very nice way of using this technology. And this is the same software, right, that we used to look at a chromatogram, at spectra, at plate reader data, and so on. So that's the power of the standard, where I really see us making a big jump towards this lab of the future idea, that I get to look at the data from all of the different experiments that I do around my samples and consume that on the same platform. And we happen to be doing that in the cloud with the tools that we provide, but you may do that on premise, you may do that on a mobile app, and wherever you need that data. That's the promise of the lab of the future, that I have the right data and I don't have to worry about how I got it, and the environment just provides it to me and makes it flow. In this case here, we've got a different data set which comes from the biologic space. So this is antibody purification done on an FPLC. And in this case, it was an ECTA unicorn file from GE Healthcare. that was converted to AnIML, and this is what that looks like. So I have these thumbnails of the different detectors that I have attached to my chromatography rig, and I can see those directly. And when I tap on them on a touch screen, or if I click on them with a mouse, they go full screen, and I can actually go look at them in more detail, or overlay them, or create reports, and so on. And this is, again, the same tool. Here is an example of mass spec data in AnIML. And in this case, the data set comes from an Agilent mass spectrometer. And there are also converters for taking that data and putting that into AnIML. And there you see at the top, you've got your total ion current chromatogram, the tick. And I've clicked on the first peak here, and I'm not sure whether that comes across really well, but you see a little vertical marker where I clicked, and then it pulled out the spectrum underneath. That's just in the web browser again. And now I've taken a different viewer, but still using the same data format. I've loaded an NMR data file, so I can use AnIML also for NMR data. In this case, the data comes from Burkhard. NMR, in this case, the Topspin software was used to create it, and it was converted. And so I have my FIDs and I have my spectra in here. And this is actually an interesting combination of multiple techniques in the same AnIML document. This is looking at a cell culture where I have bioreactor data from a Sartorius bioreactor controlled by MFCS Win, but I have put that together with in-process analytics that I collected with Roche ZX Hi-Res, which is a cell analyzer. So I got my cell counts for that, and I've put that into the same AnIML document. So now I can trend these different features of the batch inside the same view. That was really hard to do in the past. People were using complicated Excel spreadsheets to do that. And here this can be done quite easily. You can have a single AnIML file for the batch. You drop in your bioreactor data, your in-process analytics data. It snaps in on the timeline. And you can add your external analytics data too. So if you have HPLC data or SDS page or Western blots, or so, they can go into the same AnIML document, and you get a great reuse of the tools. And to me, that is also lab of the future. So those were a couple of examples of the data packages you can then actually generate if you follow that integration approach. And you can mix and match. So you can say, oh, I just want to do my instrument control, then I can use SiLA for that. Or maybe you're not interested in control, but you only care about the data. You can use AnIML for that. You don't have to switch your entire lab. You can just take one instrument and play with that a little bit and see where it actually makes sense. And it's never a huge deal and huge effort. And these things are quite easy to put together. So some key findings. Again, I'll reiterate on a sentence that I said earlier. We're in it for the data, right? That's why we're in the, we care about the results, and we want to make that as accessible as possible so that those results can generate value and be reused and shared with people. And the lab of the future is digital, quite clearly, and it's based on openness and on connectivity. And we've seen what can be achieved if we actually follow that path. The third point, AnIML and SiLA, we've seen that they work together very well, and they can accelerate these types of integrations and the collaboration between those different pieces. So if you have any questions, feel free to put those into the Q&A panel. Thanks so much for your attention and for attending this session.
Thank you, Burkhard, for that informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on your screen and click the Send button. We'll answer as many of your questions as we have time for. So let's get started. Our first question is, how can I get my instrument data into the AnIML format?
That's an interesting one. It's a bit of a chicken and egg question, right? Because obviously we want vendors to support this format and to provide that as native output from the instrument. And we are seeing a number of instrument vendors do that. SciEx, for example, is great at that, and a number of others. And we are seeing LIMS companies such as Labware and a number of ELN companies actually jump on the bandwagon here. But if your vendor doesn't do that, then there are still third-party tools that can do that. So at BSSN, we've written a library of about 150 of these to get the big things covered. We obviously hope that this will no longer be necessary in the future, that these things will come from the vendors. But if the vendor doesn't provide them, you can go to a third party, or you can even build it yourself. It's just XML. There are different avenues of getting your data into AnIML.
So Burkhard, what are the vendors saying about SiLA and AnIML? And are they open or are they afraid?
It goes into the same direction. Yeah, obviously there is this traditional thinking where if I keep my data formats and my communication protocols closed, the customer will have to stay with me and keep buying from me, because basically their data is locked up in that proprietary container of mine. And I think that's a thinking of the past, because openness is rewarded by customers. So we see quite a few vendors jumping on that bandwagon because it allows them to also generate new revenue streams, right? Because if you open up and you provide tools that are open, well, let's say you're selling mass spec software. Suddenly your software will be able to work with data from a different vendor as well. So your market opens up. Or if you're a LIMS company such as Labware and you are in the business of ingesting data, then obviously reducing the number of interfaces that you need to support is a direct impact on the bottom line. So so AnIML and SiLA actually deliver business cases where the people who adopt it can actually get away cheaper than in a proprietary setting. And these are the avenues that these communities are pursuing. There are quite a few vendors who are skeptical in the beginning, and some that will probably never open up. But over the past few years, the scene has changed and people are becoming much, much more receptive. So I think the time is now to also talk to your vendor and ask about these two in particular. Because XML, there are thousands of tools out there, literally. You don't need to license anything in particular. There is no royalty, so the cost of entry is very low. So talk to your vendor if you'd like to see this in their products.
Our next question: what about the Internet of Things? Where do you see this lab going?
Okay. Internet of Things is one of those buzzwords, right? Where we have these connected devices, and I think we all have some of them. So I think my vacuum cleaner even has Wi-Fi these days, which is kind of crazy. Just the fact that I connect something to the internet doesn't mean that it's better than before. And in the lab, basically what this IoT thing means is I'm not delivering anything that I can't do when it's on premise. It's pretty much an acronym for offering something as a hosted service. So that I have hosted application platforms which do have a tie-in to the instrument. So I have something that runs on premise, which I can then use and connect the instrument to, and then I have the actual application running in the cloud. And yes, strictly, this is Internet of Things. I think that's a term that's being overused a little, but maybe I should be saying it differently. The lab of the future is all about the Internet of Things, because I mean, anything that has a network port. And SiLA is actually being used as a communication protocol and I've seen a couple of prototypes where this has been used. There was also a hackathon at the Pistoia Alliance conference a couple of weeks ago, where a group actually built an IoT platform that connected some on-premise devices with some services that were on the cloud and took the result and presented it locally again. So Internet of Things and Lab of the Future, I guess the short answer is yes.
And Burkhard, it looks like we have time for one more question. Are there any regulatory implications when using standards?
Regulatory implications, that obviously depends on where you work. So if you're in a regulated environment and you fall on a GLP or GMP, or if you're subject to 21 CFR Part 11, these exact same rules apply. So there is nothing different here. And you have to have the same type of validation that you have in a traditional approach. Now, some standards are built with compliance in mind, and AnIML is one of them. So for example, AnIML supports audit trails, and it also supports digital signatures. So that's kind of a sweet spot, because you have a data format that's XML-based, which means it's human readable, but that also means it's manipulatable. But if you put a digital signature on top of it, you can prove that the file has not been manipulated since it was created. And that way, the instrument can actually sign for the content it created. And in a number of jurisdictions, that digital signature mechanism that AnIML uses is actually equal as a handwritten signature. And that gives you a very nice way of achieving compliance by demonstrating your chain of custody of the data and building a nice data integrity story.
I would like to once again thank Burkhard for his presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through August of 2018. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us, and we hope to see you again soon. Goodbye.